I'm very glad to here to share some of our research. People hear me okay? Hear me okay? Yes. Yeah. So I quite like the idea of having a small dedicated symposium about continual learning. This is really timely and also quite important for academics, as we just discussed that. Sometimes academic we don't really have a compute. We have to find a way. Say we still do AI, still do learning, but without gradient descent somehow. Can we do that? So my talk gonna focus on what I called learning by stateful reflection. So we're still working on foundation model, but somehow do it in a different way. And when I say continue learning, so I just write down one sentence really to say, the key message here. So the key message or key solution we figured out is that the continue learning, if you want to continue learning, but without gradient descent, meaning that without update the parameter of the foundation model, can we still able to, make a learning possible? So how we do that? We basically say, iterate reading from the iteratively reading from and writing to this memory, right? So the subject gonna be the content in the memory, and we through the read and write process, and I will show in fact it's a reinforced learning policy iteration, and because of that you can actually learn during the process, and also it's quite effective because they make use of the capability of large language model give us, which is the reflection. So my talk gonna split into the few sections. First, I'm gonna quickly say, the what is our base, which is large language model, and what would be the capability that we can make use of, and then we'll propose some of ideas in terms of these continue learning, or in terms of this idea called learning by stateful reflection. What I do is, to explain the journey that we have been for the last, 2 years also, in terms of how we gradually develop the idea, starting very empirical study to some of the theoretical study, and then beyond. And at the last of it, I'm gonna quickly give us a sort of update of ongoing work, not finished yet, but just give you an idea what we're looking for, what I called large discovery model, and then how we apply that into AI for science setting. So this is sort of we just recently released this paper to arXiv, because I think we've been working on quite a number of, in fact working on it for 2 years already. So the starting idea of this was to really sort of theoretically to really understand the generalization capability of large language model. We try to using like a traditional, learning theory, like a pack learning theory, in this particular case, pack Bayesian, to really understand what's going on in the large language model, pre-training, SFT, and then deploying, and try to say, do we have some sort of a generalization? So we are, in the very beginning, the title wasn't like that. The title is something like, large language model is a general purpose learner. Then through the analysis, the conclusion was quite negative. So then we just had to say, actually, there's a limitation. So the limitation, in fact, we do sort of analysis from, multi-agent and also this pack Bayesian to say, the training, when they do the training on pre-training and meta-training, based on the existing data, and then when you deploy, if this is sort of quite different compared to those statistically in terms of the data, there's a problem of alignment. Because of that, you cannot generalize to some cases, which is what we discovered, right? It shows very, very good in generalize various things, but if they haven't really seen the data, they cannot able to generalize that. So still have that fundamental problem that we have in machine learning. And I mean, this has become quite obvious. If you, I don't know whether people being, using Claude to try to write a paper or try to sort of, draft ideas, etc. So you find that, I mean, it's very good for now in terms of give us ideas. Some papers, some people even try to propose can we let AI to write research paper for us and to even conduct SNP. So I also use the Claude to do a lot of iterations, but I find that they can write quite nice kind of like a triple AI paper on the surface. But if you look at the actual detail of it, they don't have innovation. So in other words, they reach to the local minimum after a few iterations, and then they start to there say, actually we have this version 25, and the version 25 is the same as version 22, and this is what we got. But then you go through the paper, you find, in fact, they stuck to there. They don't really know to innovate in terms of what additional novelty that you can introduce from this paper. Human have to guide in terms of novelty. So this is why a typical example say, they only based on what they have from those two cases, they cannot generalize to something they never really be able to see. But having said that, I mean, for the last couple of months, people see huge progress in terms of coding, right? For software engineering and data science, I think that's where it's worked quite well. So that leading to my the key research thing or research topic is that how can we sort of allow these foundation model after pre-train fine-tuning, are they able to continuously learn? Okay, are they able to, when encounter this new task, which is quite different with this, can they still keep improving? Okay, so I think that's very important because we cannot get rid of the reality, this large language model everywhere. So we need to make use of it as a prime. But on the other hand, we need to have a new way to do the learning. When I say new way to do the learning, it's because of there's a few things. If you think about continual learning, that means that we cannot have like millions of samples to feed to them and using gradient descent, because you expect that after a few iterations, getting the feedback, they would able to improve, right? At least, or hopefully solve the problem at hand. But just few feedbacks. So if this is a goal that you want to achieve, then back propagation is not a good way, at least at the current form, because it's extremely inefficient. You have to rely on millions of samples to get it to work. I know a lot of fine-tuning, a lot of research on this fine-tuning, because I think if you were working on that, it's going to be very limited. I mean, I see a lot of research work, like even in the academics, they try to fine-tune this. They cannot do like 100B. They're working on, working on 5B, and then fine-tuning is better than, 100B, not fine-tuning. But this research is quite limited. Only lasts for maybe for 3 months, and after 3 months, people won't be interested because then this 100B models suddenly become much better because they receive all this data, they can do better, and then your research become meaningless. So that's why I think I like the idea of this hypothesis working on continuity, because we should work on this. These other places, all this foundation model, they don't do, right? They have a huge money, let them focus on this. As an academic, they focus on this. And without using gradient descent, without using Bible corporation, so can we have a solution? So my answer is yes, because you can think about this, is that, then perhaps the only way is that you're not fine-tuning it, but make use of something else, which is a memory, and also reflection. So I just want to go back to to the fact that if you still based on large language model, what kind of thing they bring us, which is otherwise we wouldn't get from other kind of solution. So starting with like the early stage of this, ChatGPT, I think it was 2020. They had this GPT-3, and in that paper they basically show, ChatGPT or GPT is a large language model is kind of a few short learner. I think I was intrigued by the paper, the result they show from OpenAI, because they basically show that they have this sort of in-context learning capability. So I think that they illustrate one example. They don't have like a specific training for French to English translation, but they give a few examples of French English translation. And Lex token, you give them a prompt, you give them French, they will automatically translate to English. And in fact, it doesn't really matter the example is correct or not. Sometimes you give the wrong examples, but the format is correct. Then you somehow trigger the language model to understand that actually now you are trying to do machine translation, particularly for French to English, and then you will automatically get a correct answer. I think it was a surprise to everybody, because this is I think this would potentially change the way we see learning, because we used to see based on what our analysis like pack learning, all this stuff. You need to have some sort of non-sample complexity. Like you need to have statistically, you need to have a quite large number of data set, and you try to see this mean prediction, what I call a mean prediction, like whatever regression you build, is how this mean deviate from the the other statistics, like how deviated, and based on number of sample you got, and that mean gonna be deviated from it. So that's where the fundamental pack learning is really about. But here it's completely different, because they only have a few examples. They were able to solve the problem that which otherwise they cannot solve. So as this is a starting point, and later on we can find that in fact we call it feedback-driven reflection. So it's nothing but say you give them a particular coding task, and they will generate result. And to compile it, maybe it didn't work, and just trace, using that trace as feedback. You don't need to even have a reward, but treat it feedback, and put all together the prompts, and they will generate again. And then this time maybe highly probable they will generate correct one. Maybe a few iterations until they can solve. So I think this is sort of slightly better setting, or slightly more stronger setting than this, in the sense that this is a human give, right? Human give them a few examples, a few short examples. This is the environment give them. And then the third one is so-called chain of thought. You don't give them anything, but you ask them to say, can you solve step by step? Can you generate your own token and give them more compute? I mean, that's a different way to look at it. It might maybe because give them more computation power, right? Or give them sort of internal reasoning. That's a different way to look at it. But I think if you look at this trend, is that without even feedback, but they somehow give them their self-critic feedback, and or calculation, they would able to do something. Without it, compared to the one without it, they will highly probable they will produce it. So I call this generalized reflection. In these three of cases, they have a common thing here is that instead of directly produce result, give them something, right? And in between, let them retrieve something, kind of I call it experience. This experience is coming from human give them, right? They somehow interact with the environment, or some experiment from, I don't know, embedding in the language model itself. And with this, they do reflection, and then hopefully they'll solve the problem. So I think we got this very good base, is that we have this intermediate step that give us the hope we can allow them to learn, and then learn in an efficient way. So that's sort of a architecture we draw about the way, what I call state, when I say stateful reflection. This is what I mean, is that you give the question, okay? First things first is that you're gonna fetch it from, we can construct some what we call episodic memory, which store your past experiment, the agent experiments, large language model experiments. And you do the read process. In other words, you sort of fetch the relevant experiments and do the reflection. What I refer to reflection is nothing but here's a condition on this, can you generate your answer? Okay, and then interact with the environment again, and we see all kinds of feedback, and somehow write it back to the memory. Keep doing. So this memory, maybe in the very beginning, is nothing there or not relevant content there at all. But after a few iterations, you might populate with some sort of relevant ones, and eventually they would be able to solve the problem. So I think that was why we thought maybe this is very good architecture to sort of allow agent to learn. So the, I mean, this is what I draw maybe I think later last year, when I have the second paper about it. But this was in the very beginning, we have this ICML paper. At that time, we haven't really even think about this at all. What we think about is that the specific task is the following. Yes, specific task is the following, is that we want this large language model to generate code for us to do data science problem. And this data science problem is they have to generate Python code for it. For example, say I got this particular task, say, let's say Kaggle, okay, give them a description about this particular task, or send them the data, and let them to generate code, maybe build a prediction model to predict, weather, etc. So that's the setting. So then, obviously, we don't really have compute, as I just mentioned. We don't do fine tuning, but can we have a solution of it? So that's why we figure out, say, maybe we should do this, which is a sort of old, method called case-based reasoning. But if you go through this case-based reasoning literature, quite old idea, but there's no mathematical formulation of it. What they actually have is this kind of they call it 4R cycle: retrieve, reuse, revise, retain. So, given that new problem, they try to retrieve the from the previous cases, and then try to revise that based on the previous cases, and then deploy to see whether they will work or not. Then if it works, then they will put it back in the case bank, and then keep growing this. So I think this idea, and people demonstrate it works, but never really sort of demonstrate. Because my PhD a long time ago was really about collaborative filtering. So this sort of idea, the case-based reasoning idea. And Xiaoxue, I think you also thesis also collaborative filtering, right? So this is a sort of a have the same idea, like a previous case, similar users, and retrieve their ratings using that average and become your prediction. So it's kind of memory-based, and it's case-based sort of learning. Only in the collaborative filtering you have a mathematical formulation about it, because in that specific case you can, because you do rating prediction, so you're basically averaging from your neighborhood weighted average, and then you make a prediction. But in other case you cannot, particularly in the code base. How can you know? One difficulty is this: how can you revise it? You have to ask your human to revise it, because without a large language model. But at that time we thought about, if you combine this case-based reasoning with large language model, maybe we can sort of using large language model revise it, and can make everything automated, right, end to end without human involvement. So this is sort of idea, and then there's a lot of other work about the rack. So this is different. I mean, although we're using database, right? We retrieve things, but I think this is fundamentally different because we try to figure out the learning, right? We make use of database and retrieval stuff, but the idea is that And we try to figure out this online learning as our, a problem. So this is sort of a task the first task we do is to say, give them a bunch of data set and, give them instruction and then let them do it. So we find that interestingly, and also to our surprise, we're using this GPT at that stage, I think GPT 3.5, GPT 4, and put it in the memory, and then generate and see whether it works or not, and then until. So after a few iterations, we find that in the very beginning, they probably wouldn't be able to work, but after a few iterations, it works. So, so we are, this is also like a small scale test to show that in fact it's better than the other, baseline thing. So we feel we got an ICMA paper quite nice, but then we think about maybe we should do something much bigger. Okay, not just the small scale data set. Can we do something bigger to see whether we would be able to solve, a data science problem once for all? And then the obviously setting is Kaggle. If you're able to deploy a large language model as sort of case-based way of doing it, and to show it's better than human in terms of solving data science problem, I think then we gotta hope to solve it, right? We gotta hope to solve data science problem, and maybe give us Nature paper. So that's the 2 years ago that our idea. So then this is work with Huawei London lab, and they also get very excited by it, and then have a bunch of people who work together on this. And by the way, the guy working on this, he actually left to Meta after this work. So it's very good to work on Kaggle, because if you look at it, there's about 300 people Kaggle recognize them as grandmasters. These are the very good human beings in terms of their solving data science problem. So we basically built this what we call Agent K, continual learning agent, to participate on that, to basically have a ranking compared to human. And that would be good then for us to say, if we were better than those people, and then we can claim we solve this data science. So this is just give you an idea what kind of typical data science problem. Like in this particular case, it's called right whale recognition problem. So this is a marine biologist. They have a data set of the right whale, and they actually annotate in terms of who they are, because in the world there are only 1,000 of them, right? 1,000 of them, and to give them a name. So they want to say, I got this annotated data set, and can you build a predictor? If I took any photo of them, I would immediately recognize who they are. So that's the problem. So to give them the description of the problem, throw away the data set somewhere. And so this is our starting point. Say we just give them the URL of this. That's it. And then they will find a way to download it and do a whole lot of things. URL, data scraping, getting the data, cleaning it, feature engineering, model creation, everything. Okay. And they're allowed to use using any arbitrary tools. They are allowed to fetch the internet to really understand what question would be. Remember, that was 2 years ago, not now, right? Because now the model is much more, better. So then we encounter a big problem at the time, is that this is quite long. Okay, some difficult problem. They might last. You have to run all the things for maybe 2 weeks. So the large language model not able to, given the context, even 1 million tokens, they cannot solve the problem. So we basically think about maybe there's a bit of sort of at the time I think I worked with UCL neuroscientists like Neil Fergus. We're working on this neuroscience. We think about this consolidation. So the consolidation is like a human. Every night when we sleep, in fact, we consolidate our memory. So in other words, this episodic, the content in the episodic memory into the somatic knowledge memory, where maybe you forgot what exactly happening at that day, but you generalize it. And sometimes we recover what happens in that particular day. So sometimes you make a mistake in terms of actual things when you remember things. So this is what happens in human. So we in order to solve this long context problem, so we do this consolidation as well. But I mean, to give the theory, because we need to write a paper, so we have to get some theory. In human learning, also do some kind of conceptualization. But in fact, if you think about this, the actual coding, what we do is that we consolidate, is that we not store everything. We not store the, like when we, for example, in this particular state, or maybe in this particular state, we not store all the code empirically, but rather ask them to summarize, give them sort of say, what you got so far, what's a good thing, what's the best thing, record this, and then continue doing it. Then keep time, occasionally do the consolidation. And we solve this long context problem, and they allow them to run entire process without any problem. So this is sort of demo that we got to show you. So by the way, it's open source, so you can actually have a look to see whether that will work. So yeah, so this is where we show that they can actually work to run that. So we do the some analysis, and this is all the tasks that we tried, and when compared with humans in terms of the performance they got, and these are the one we can actually got this gold medal based on the criteria from Kaggle in terms of the whether you're gonna be a gold medal or not. So we in total, I think we got this. This is not, maybe it's not latest one. I think we got this 9 gold medals in Kaggles. As long as you got 5 gold medals, then you deemed as a grandmaster. So look at the statistics, compare with all this grandmaster and the other, and we are actually here. So it's better than the mean of this master, and we granted this grandmaster. We're not in the mean of grandmaster, something here. So I think we can reasonably to claim that we solve this data science problem end to end by using this sort of, case-based kind of reasoning, kind of methodology. Any questions so far? Okay. So, I mean, maybe I can quickly go through. So then we try all kind of things. For example, we try this automated software test, like you give them testing tent. This particular, say, you want to do the test, and they will generate code for it. Right? This they can use in this, retrieve, reuse, revise, retain kind of methodology. And that's how we start to really sort of formulate what do we mean by case-based reasoning. And so maybe I just skip this. So it works. And then, so in this paper, I think still under submission, is actually we mathematically figured out that, in fact, I will just show later on how we formulate this. So we have retrieve, reuse, retain, and the key things what we find is this how we actually retrieve the case. Later on, I will show you that. In fact, this is retrieve, this is read, is kind of doing optimization, doing maximization. Because you're doing maximization, therefore there's learning involved. And this particular one, still under submission, is that we actually using bandit. We formulate this kind of case-based reasoning as kind of bandit problem, and we show that in fact what we construct is these two regret. Number one is sort of retrieval regret. That is where we try to optimize. And then another one is called coverage gap. This is sort of something coming from the large language model. If you think about this, it's really true, because then when you get in the previous case, it's like you find the neighborhoods. And this neighborhood is not necessary to be exactly the same as yours, right? Otherwise, then you got the previous exactly solution, you just give them the solution, right? It's not really learning. So the real learning only happens is that when you get this neighbor, and you generalize it from the previous neighbors. And that's a capability from this large language model. If the model is very powerful, even all these examples are far away from it, they can still solve it and generalize to the cases which is far away from their previous experience, right? If this foundation model is really, really kind of stupid, even though it's very close, they cannot solve it. So I think that is where large language model companies like Claude and all this, they need to figure out this. And for us, we really forgot this. We need to figure out this retrieval request, right? And try to find a way to what to mean by similarity and all this stuff. So and then after this Kaggle competition, we think about what kind of agent problem, agentic problem we try to solve. So there's some this kind of Gaia leaderboard, if you recall, last year. So it's a very challenging problem. They basically give them a bunch of tools, and then they have a 3-level of problem, and let them to search the internet to find a solution. So we work on this, and we're using this sort of memory-based ideas, right? And to formulate, we start to try to formulate it now. So, and then the planner basically is using some kind of sort of an idea. So then we create an idea called Momental. That's where we really think about, yes, actually, the case-based reasoning that we do is in fact a reinforcement learning approach. In fact, we are using reinforcement learning to do it. So, and this paper is getting quite popular last year. Maybe I think we got title. So this is really like a pain point of industry, that you try to learn, you try to build an agent which you want to fine tune, but you don't want to touch. You can't touch, right? Or model parameter. And we show that in fact in this particular paper, we nail it. We are basically #1 in the Gaia leaderboard, and in terms of the performance. And you can show that in fact, in the very beginning it's not, but with this, so-called case-based reasoning kind of thing, and it works. And there's a lot of buzz about it. But I think it would be good that if because this is open source already since last year. So if you're interested on that, then please have a look, and maybe you can use it for in your case, Oracle people here, then maybe you can plug into your database and see what happens. Because I'm quite keen to, try various of cases. It works quite a lot in the code generation, data science, law cases, retrieval, question answer, agentic problems. A lot of cases we tried it, it works. So I mean, if you guys are interested, I'm more than happy to have a chat. And so, so what is the math behind it? Then we try to figure out. Sorry. Okay. Yeah. So what is the math behind it? So then we write it down as some kind of Markov decision process. This is like a typical. The red one are the typical Markov decision process. You got a state, action, reward. State, action, reward, so on. What we actually adding is this memory bit. Okay, these blue ones of that. And so if you write down the whole chain of these probabilities, so tau is basically the trajectory that you got. So in fact, they construct into retrieve, the nice thing about large language model, it can, based on the previous case, they will generalize your new solution. So it's called reuse and revise, which is very nice, which you can't do it without large language model. And evaluation, retain and put in the memory, and the transition go to the next stage. And also interesting thing is that the policy become composed policy, meaning that you want to, given the memory, you want given current state, you want taking sort of a decision, right? And that would decompose it into first mu is sort of retrieval policy. You try to, given current state, retrieve the case, and then conditional case, you large language model to reflect. So basically, you have this capability. So the nice thing of this is that if you are like a big company, you have a facility, luxury to optimize large language model, you can do that. Right? If you don't, you can fix it, you optimize this. So by doing this, you basically become the program into continuous learn, and also maybe this is slow learning, right? This is fast learning that you're able to do. And this then we'll continue sort of, and last year continue sort of think about what is behind. So I think I sort of figure out is that this is the same thing as what I just showed, but to make it much clearer, say memory updates, what actually happens. So basically say given memory, given state, retrieval case, and that language model generate action, you go to that bit. And then this is again, the problem of this is that this is not Markovian anymore because of memory that continuously gather all the historical data. And so you bring this Markovian property of it. But the nice thing is that if you think about this, this is an internal agent state. This is external state. You combine together as one state. Then it's become Markovian again, become Markovian again, what we call the reflected MDP. So given this is sort of MDP, and the original one is not, and then you become MDP, and then you can apply all kinds of nice reinforcement learning solution for that. And basically in that paper we just showed that, in fact, you can come in with policy iteration, and this is nothing but implementing a nice like a read-write process. As long as you do the read is nothing but you maximize a sort of a regularized reward function. You create a nice retrieval, okay? And the writing is nothing but policy evaluation, because each time you get a feedback, you know in that particular state, that particular action, what kind of reward you actually have from the environment. So it's kind of policy evaluation, right? And then this is a policy maximization, policy evaluation, and create some kind of. So it's quite nice, And also this is sort of the same thing as before that. This is sort of you retrieve the good ones or bad ones in this particular circle, right? And the large language model allows you to generalize. So basically, have a tool part of this. So in conclusion, and how much time do I have? Yeah. So I still have few slides. So in conclusions, empirically, continual learning by using some kind of case-based reasoning kind of methodology is worked quite well in number of cases. And we showed, in fact, read-write process is equivalent to policy iteration. And now, if you academically, we want to improve is that maybe policy iteration is not the practically useful. Maybe there's other way to think about new algorithm based on what we just formulated. So I think we'll be open now a lot of research questions here, and also sample complexity we need to theoretically figure out, and also discovery. So discovery play a quite important role, which I'm going to talk about. Because when you do the reflection, it might be hallucinate. Whether hallucinate helps or not. So I think this is connected to the discovery, which maybe I'll just give you a very quick update. So this is sort of latest update on this momentum series is that, in fact, if you think about using memory, Claude do the same thing. But they didn't really realize what happened. But maybe they realized, they didn't really show it, but they're using different way of doing this, that the memory, they're doing the memory, but in the markdown file. So we think will be very good that let this read-write process to hook with the industry in practice. So that's where momentum skills happens, is that maybe the memory, we're not gonna put it in a rack, but we consider it as markdown files, right? Whether that would work. And this worked brilliantly. And we go back to the Gaia database, the Gaia challenge again, agent challenge again. And you find that using scales, and we don't even need to devise an agent specific for that particular problem. I think if you recall what we did asked about the Gaia, in fact, my students work, very hard on 3 months to figure out solution for it. But in this case, we don't, right? So what we actually have is that give the agent these 5 elementary skills, like for example, download, capability of download, capability to the search, capability to read a PDF file, etc. And they will create additional skills and solve this Gaia problem. And they will create these additional skills, solve this human, last evaluation problem. I think this is really open up a solution, allow this agent to self-involve. And also, we can do the multi-agent because we figure out the learning, right? We can use still the same memory-based sort of learning to do the multi-agent. Then let them figure out the large equilibrium, let them work together. So this is sort of an additional paper we worked out is to, deploy, in this particular case, I think it's 7 agents, but we can actually allow 20 agents work together to solve one particular task. So this is the technical detail about this. Maybe for the remaining 2 weeks, 2 minutes, I will go through what's next. And I was thinking about how to combine this sort of large language model as a prime information. Remember, we're talking about this, slow learning using gradient descent for the one, and also this quick learning with this sort of episodic feedback. Can we combine this all together? Then we think about this sort of what I call large discovery model. Really try to say, if they encounter something completely new, are they able to quickly, through future iteration, to link to it? I think we will just quickly talk about word model. I think we need to build a model-based solution. In other words, we need to sort of build a model for reward. And previously, we just get a feedback, right? So can we actually have a model for the rewards? If you're doing that, and then this sort of generate from the language model, and then we come with very good way to generate the policy. So we're using one of our old technique, which is Bayesian optimization. We're using Gaussian process to suppose this F is just reward model, right? You want to find the policy or the solution which is going to maximize reward. So the Gaussian process quite a nice way to consider as a black box and build a Gaussian, Bayesian optimization consider as a sort of black box function and build its Gaussian process for that. It will be much more efficient because using linear variance to guide the exploration. And we're heavily using all kinds of science problems. And we were, in fact, have a technique which is like one of the best Bayesian optimization techniques. So that's why not we combine all together. So if you fetch this paper is highly cited. I fetched the people using our packages and find that people, like this is theoretical physicists using it for, conduct their experiment, hyperparameter tuning. And this chemists and also these biologists using it for, automate their laboratory experiments. So then we come with sort of idea, say, actually we should combine with larger language model as sort of, I call it reservoir. So in other words, that they have potential solution. but maybe hallucinated, right? But we consider at the back end, that would be at least better than my random computation. So, and then we got this front end with using Gaussian GP to build a surrogate model for the reward, and then keep updating them. So then we got this quick slope loop, which is sort of update this acquisition function. Acquisition function can be here, and then we build this sort of a policy which is based on large language model solution and ranked by acquisition function. And then this is sort of quick loop to update this acquisition model using BO way of doing it. And this is sort of long term, say maybe we can build a context, and this is memory, you can using it or fine tuning large language model. So we have an initial try. Because if you need to connect with hardwares, I find this is going to be maybe the next really big thing is that we cannot do everything digital, because everything in digital eventually can be conquered by all these big, cloud open AI companies. We have to go to hardware stuff. So I got contact with some of these drug discovery companies. They have this old beautiful machine, can do the experiment for like a 1 day, thousands of experiments. So we're plugging this like a BO large language model and do that for them. So the idea is nothing but search problem. Think about the drug. It's really like a combinatorial optimization. Try the combination of these molecules and then treat some, have very nice treatment. So some cancer problem. So this is one case I find very useful. Another is sort of capacity. I think maybe you read this news article about they automated 700 experiments, with 2 days, large language model reflect to do that. So we're using our techniques, because I think that this case is very easy. In fact, we do much more advanced than that. But I just want to show this large discovery model works quite well. This is a result, in fact, I fetched this morning from my student. They tried this Apache setting. This large language model reflect and using BO to adjust what kind of solution they got, and can easily get this rank number 1. It's largely much better than all the previous solution. And we do more than that. That's why I tried for last half year also. We in fact work with some of these chemists. Really have this hardware. So this hardware they already have it. And we do BO, Bayesian optimizing, build this sort of surrogate model, and also this haven't really plugged in this large language model yet, but we are in the stage of it. So if you look at this, this is the best solution. Each point here is one experiment, and they have a 2 performance. These are the ones that the best performance solutions discovered by our agent. Okay. So I think with that, I will conclude my talk. Thanks for your attention.
Excellent talk. So, are there any questions?
Thank you for your talk. One question about canals forgetting, because that's normal problem in fine-tuning how that works in continual learning. Is that going to be an issue?
Yeah. So people talking about for example, Google have this recent paper or serious paper about this. They call it test time learning, right? Test time. So they have some kind of still using gradient descent, but adjust some of the memory bit, and then to see what happens. So I think that's the way people doing it. Still using gradient descent to say maybe I have a few. A number of examples, maybe not millions, but could be thousand, could be hundred of, whether I can still able to adjust it. So this is sort of a test time, sort of a training, right? People using it, and it works in Arc 3, Arc 2, I think. Some people use the technique on that particular case. I think it's possible, yeah, and maybe that's a combination of different techniques. I think that that's a different way of looking at this. Yeah. I'm not sure whether you try this Arc 3 as some sort of test bed. We tried it. It's really, really hard. I think it's really, really good continual learning benchmark people should try. they also have a computer vision element of it, because you need to understand the game itself. So basically the ARC3, for people who don't really know, I think it's a guy behind it. Well, I mean, this is quite interesting data set, because ARC2 was used by ChatGPT to demonstrate their super performance. I think ARC3 become much more difficult, and all the people sort of jump into it to try to solve it. So this is really completely like a pure continual learning problem. So this is sort of giving you a set of games the agent never really see before. They not really tell you what the purpose of that game, right? And that agent to explore that and find a solution. They have given you some public data set, like 25 games released, so you can play around it. But when they test it out in the Kaggle setting, you never know what kind of game this agent gonna encounter. So I think it's only allow a few iterations to understand or even play successfully on that against the human. So I think it's really good continual learning setting, and maybe worth exploring.
Thank you.
Thank you for the very interesting talk. So I was thinking of some kind of adversarial attack scenario. So if a new task was described like intentionally to be as similar as possible to the existing task,
Yeah.
so what do you think the model would behave in this kind of scenario?
And what kind of scenario? So
If a new task is described intentionally to be as similar as possible to the existing task,
yeah.
then what do you think the model would behave in this kind of scenario?
So if it's similar, then it might be easy to solve.
But I meant such task that the solution should be fundamentally
Okay.
different,
Yeah,
like
yeah.
described.
Yeah. So
intentionally.
yeah, you're right. So I think that's then it's very good sort of setting where you figure out what will be the best retrieval, meaning that what kind of similar cases that fit to that fit to your new task, and then I would hope that retrieval model would figure out that similarity matter. Therefore, say similar case would have a similar performance.
I have one last question. So I want to ask, you mentioned this memory policy for the retrieval part. Does it involve grading?
Yes. It does. In fact, so there's a two way. Number one is that you have a tabular queue function. So then in that case, you have a limited number of cases. And it's a discrete, like a reinforcement learning kind of case. Therefore, you're just building this tabular solution. That's it. But then you could have some sort of model to approximate this tabular queue table. In that case, I think what we did is that we're using some kind of BERT model, like a simple, you got this textual data, and then you've got this sort of embedding, and you make using this embedding to build this queue function.
And are you fine-tuning this?
Yeah, you're fine-tuning that. So yeah, I think that is possible, because then that typically is very small, like network. Usually it's already tuned in terms of similarity. So you can immediately use it, or you fine-tune it a bit. Yes.
Do you have any mechanisms for memory pruning? So I notice you keep adding stuff to memory, but sometimes
Yes.
it's important
Yeah.
to forget about some spurious thing.
Absolutely. So this is I think it's a really good question. So you can think about this like a cloud skill markdown as kind of pruning. So rather than episodic memory, remember everything, you actually generalize it, say what would be the principal rules or some example code behind it to guide them to do it. So this is some kind of pruning, if you like. So we were thinking about from episodic memory to semantic memory, and then you can actually keep updating it. So I think this is a very interesting topic. We haven't really, we only allow large language model to sort of say, you do the work, but maybe there's a way to have a better way of doing it.
memory becomes bigger and more generalized, then do you still need really large language models, 400 billion parameters, or can you rely more on the memory to use a smaller model?
Yeah. So. Yeah. So. How many try? Like so far we got is 1,000 of records in the memory. We haven't really tried much bigger than that. So yeah, I don't know whether in the future they need that. But I think that also related to the question about the consolidation, right? If you have anything beyond that. So far I think 1,000 of it, there's no problem to not build a module on top of it. Yeah, but maybe longer, much larger than that. That's we'll do something different.
Thank you. Okay, let's thanks again.